Hi there and welcome to video number 12 in our series on the calculus of variations. In this video we're going to re-look at the Euler Lagrange equation. The derivation that we did several videos ago was not a general derivation, it was a derivation done using a particular example and using the localized phenomena within that example. What follows now is a more general derivation. Now if we go back and we'll start off with our coordinate axis. There's our y and x. And if we look at the simple example of the shortest distance between 2 points. So here's a point here and another point there. And we have the small elements ds. Then we know from what we did previously that we can write ds in the form of the functional 1 plus y derivative squared by dx. Now, more generally, we can write the functional equation as I equals integral from x1 to x2 of the functional of x, y derivative by dx. Now, the Lagrange derivation starts off by looking at 2 points, x1 and x2, and imagining that we had a guess at what the shortest distance between 2 points was. Now we know it's a straight line, but let's say we make a guess, and there's a guess there, and we'll call that guess y of x. So y of x is our guess of what is the shortest distance between that point there and that point there. Now what we'll do is we form another equation, we'll call it large Y of x. Now this is going to give us a family of equations which are all slightly different. Now that large Y of x is another equation, another function here. Now we'll let that large Y of x equal small y of x, which is this one here, plus some other function, we'll call it eta of x. Now eta of x can be any function. Let's say for example there's one there. Now that there is our eta of x. Now what we're going to do is we want to be able to produce a family of curves that start at this point and end at that point, and the family of curves have to be able to be generated by a simple change of a variable. Well, we can do that easily if we introduce a variable called epsilon. So I'll put it actually this end. Epsilon. So this here will be a family of curves which are similar to this one here, but multiplied by a real number, epsilon. So for example, if epsilon was 2, we'd take each of the points here and you would have a curve that would be twice the amplitude, but roughly the same shape. Now if we were to take this eta of x times epsilon, and then add it on to our original y of x, we would be adding, for example, in one example where epsilon equals 2, we would be adding this dotted line here onto this line y of x. So our new large y of x would look something like that. Now that's just one curve. As we vary this value of eta, then the value y of x varies. So now we've got a method of producing a family of curves using one parameter, which is a real number, epsilon. Now, where are we going to go with this? Well, we know that if we change epsilon, our value of y of x changes. Okay, now first of all, what we'll do is we'll look at a little aside, but will come in handy later on. If we look at the change partial y by partial epsilon, that equals partial y of x upon partial epsilon plus partial, this term here, I'll write it as epsilon eta x by partial epsilon. That's going to equal, well, this term here, y is a function of x, y is not a function of epsilon, so partial y of x by partial epsilon is 0. Okay, plus, now this one here, we've got the product rule, so let's take, it would be epsilon times partial eta x by partial epsilon plus eta x partial epsilon by partial epsilon. Now again, that would be 0 plus, again, eta is a function of x, it is not a function of epsilon, so that term there would be 0, so that whole term there would be 0 plus partial epsilon by partial epsilon is 1, so that would be eta of x. Okay, so we know this fits in here, yeah, partial y by partial epsilon equals eta x, and if we were to define also partial y derivative by partial epsilon, by the same argument here, putting all the same values in other than its y derivative, we would work through the same route here and we would get eta derivative of x. So we've got this one here, okay, and we've got this one here. Right, it'll become apparent why I've worked through those examples. Now, if we are looking at the functional, which we've written up here, I is a function of x, y derivative by dx, then we know that if we change epsilon, then this value of I is going to change So what do we mean when we change epsilon, I changes? What you're saying is I is some function of epsilon. Okay, so if I is a function of epsilon, then we could work out the differential di by the epsilon, okay, at epsilon equals 0, okay, and we can set that value to 0, then we know that if epsilon equals 0, then these values here, this large y, would equal the small y, because we've set epsilon equal to 0. So if epsilon here is 0, that term disappears and we've just got large y of x equals small y of x. Okay, so then we could write this differential, this functional equation out, and we could use the chain rule, and we could write the integral from some value x1 to x2 of partial f by partial y upon, well, we'll make it large, still large y at the moment, partial y by partial y by partial epsilon plus partial f by partial y derivative times partial y derivative by partial epsilon, all by dx. Now we've noted here partial y by partial epsilon, we'll work that out here as eta x, so that can be written as di by the epsilon equals the integral from x1 to x2 of partial f by partial y times eta x plus partial f by partial y derivative times eta derivative of x, all by dx. Now, as I said, if we're doing that and we're setting epsilon equal to 0, then we can replace this y here by the small y, so we could write that at, if we write that at, that's some value at the time, if we write that at epsilon equal to 0, so epsilon equals 0, then this here becomes the integral from x1 to x2 of partial f by partial small y eta x plus partial f by partial small y derivative eta derivative of x, all by dx. Now what we can do, and what's done in the books, is we use integration by parts to split this term up. So what we would end up with is this term would remain the same, so we would be partial f by partial y times eta of x plus, now integration by parts, that'll be a wee aside here. If we say, if you want to integrate u times v, then, so if I say the integral of u times v equals u times v minus the integral of v du. Now if we let v derivative equal eta derivative of x, then v would equal eta x, and we let u equal partial f by partial y derivative, then u derivative would equal partial of partial by partial x of partial f by partial y derivative. Okay, so we can rewrite this here and split this up using this integration by parts. So you would end up with, the first term would be u times v, which would be partial f by partial y derivative times v, which would be eta x, and that would be from x2 to x1, and that would be minus, second part of it is the integral of v du, which would be d by dx partial f by partial y derivative times eta all times eta x derivative from here. Okay, now this here would be 0 because eta x is defined as 0 at x1 and 0 at x2. So this term would disappear and you would be left with this term here, which would be, that's actually, I made a mistake there, that's not the derivative of that one, that's partial x, yep, you'll notice that if you check through the working. Okay, so that's going to be partial f by partial y eta x, of course, and that's the integral of all of that as well, from x1 to x2, x1 to x2, minus the integral from x1, x2 of d by dx partial f by partial y derivative of eta x all by that by dx, and that's also by dx as well. And then you can bring these together, so you would have integral x1 x2 of partial f partial y minus d by dx of partial f by partial y derivative all times the factor eta x all by dx, and we'll be making that equal to 0. Now, in order for that to be 0, we know that that doesn't equal 0, because the whole point is that that is a function that we can vary, so that's this part of the function. It doesn't equal 0. Okay, so in order for this identity here to equal 0, that section there must be equal to 0. Now, there's a proof of that, and it's called the fundamental lemma of calculus of variations, and I'll go through and I'll do that proof in the next video. But for now, all we need to know is we've got our Euler Lagrange, which is our partial f by partial y derivative minus d by dx. Oh, I made a mistake there. Partial f by partial y minus d by dx partial f by partial y derivative must equal 0. So that there is a more analytic and more generalized derivation of the Euler Lagrange equation. Okay, thank you for listening, and the next video we'll just go over quickly the fundamental lemma, which is just a proof that this term here must equal 0 in order to make the whole of this integral equal to 0. Okay, goodbye.